Is it generally true that A intersection B union C is equal to A intersection B union C? And regardless of whether we think this is true or false, can we justify our belief? We have seen earlier that when you have a series of operations of different kinds, intersection followed by union, or union followed by intersection, we cannot just parenthesize the expression arbitrarily. The parenthesis must be supplied because the result depends on how we parenthesize the expression. So if we have an expression like A intersection B union C, if we parenthesize it like this, we might get one kind of result, and if we parenthesize it like that, we might get a different kind of result. So we suspect that these two sets are actually not the same. If we suspected that they were the same, then we would have to prove this equality rigorously. We would have to take an element arbitrarily from this set and show that it also belongs to the set on the right hand side, and vice versa. We would then take an element from the set on the right hand side and then show that it belongs to the set on the left hand side. So doing both of these would justify our belief that these two sets are the same. But in this case, we have read enough of set theory to strongly suspect that these two are not going to be the same in theory. We looked at some Venn diagrams earlier to see that the regions corresponding to these two sets are different. But when we are asked to disprove a claim like this, the best way to do so is by coming up with a counterexample, by coming up with a concrete example of three sets A, B and C such that this equality does not hold. That would be a counterexample that disproves this general claim. Now, how do we come up with a counterexample? Let's try some simple strategies. One simple strategy we could try is to just make one of these sets equal to the empty set. Let's say A is the empty set phi. What would happen if we make A to be the empty set? A intersection B would then become phi, because the empty set intersected with any other set would be the empty set, and the result would be the empty set. And when we take the union of that with C, we would be left with C on the left hand side. Now let's look at the right hand side. If we have A equal to phi, then regardless of what B union C is, phi intersected with B union C would be phi. So we see that we get C on the left hand side and phi on the right hand side. So as long as we choose C to be some non-empty set, we would get a different set on the left hand side and a different set on the right hand side. So let's take C to be the singleton set 0, and let's take A to be phi, and frankly B can be any set, it doesn't matter. So let's just take B to be the singleton set 1, but you could take it as any arbitrary set. A intersection B would be phi, phi union C would just be C. So we would get this set on the left hand side, and on the right hand side we would get phi intersected with B union C, which would be the two element set 0, 1. So phi intersected with B union C, regardless of what B union C is, would be the empty set phi. So the right hand side would be the empty set phi. And so we can clearly see here that the left hand side is not equal to the right hand side. And so this is a counterexample which disproves this general claim that these two sets are not the same in all circumstances. Of course, they could be the same in some circumstances. For example, if A, B and C are all equal sets, then the left hand side will be equal to the right hand side. But when such a claim is made in general for arbitrary sets A, B and C, this equality must hold for every possible value of A, B and C for it to be true in general. Even if there is one counterexample for which this equality fails, we would say that this claim is not true in general. And we have come up with such a counterexample.